Okay, ladies, gentlemen, well, I'd say mainly gentlemen. My name's Francesco Cesarini, half Italian, half Swedish, but I've been, well, English school when I was 5, American high school when I was 13. I've spent 10 years in Sweden, and just to mess up my accent even more, just in case you can't tell I'm Italian, I've been living in London for the last 13 years. And what I'm going to talk about today is give you a bit of the background on Erlang. Erlang, a programming language which, well, powers much more of your infrastructure than what you might know, but is not that well known. We usually say that it's a badly kept secret. How many of you here have heard of Erlang in some shape or form? Okay. How many are actually using Erlang? There's 2 or 3. Okay. Sorry?
Directly or indirectly?
Well, indirectly, I can say if you own a smartphone, there's a 40% chance that all of the data your smartphone handles is powered by a system written in Erlang. So you might not realize it, but it's powering about 40% of all of the smartphone traffic out there. So indirectly, I think everyone is affected by it. So what I'm going to talk about is, well, my history in Erlang, well, started when I was in university. And there I came in contact with this what felt really futuristic language, and it prompted me to, and I thought it was really, really cool. We had to do several exercises. We got the chance to compare it to other object-oriented technologies, and what made me realize, there was something great about it was the productivity gains I was doing when I was doing my exercises, and so that prompted me to pick up the phone and call Ericsson, call the inventor of Erlang, Joe Armstrong, and ask him for an internship. Now, at the time, Joe Armstrong was working at the computer science laboratory at Ericsson. And this here is the mugshot which they took at me the first day when I did join Ericsson, which was, ended up being on my ID badge for, well, the first year I was there. And I went in and I started joining the computer science lab as an intern. Now, the computer science lab at Ericsson was founded back in, well, the late 80s. And what they were trying to do was solve the problem of the programming language of choice for the next generation of telecom switches. At the time, they had a lot of single, vertical networks. You had your cellular telephony that went on its own network. Cable TV went on its own network. You had, well, plain old telephony, and you had internet. They were all separate networks. And what was happening, what they realized in the late 80s, early 90s, is everything was moving over to a packet-switched backbone. So what they did is they spent quite a few years trying to figure out what is the best language to program next generation of telecom networks. And they tried most languages which were available, and quickly came to the conclusion there is no one language which fitted all of the requirements, but there were a lot of really, really good features in the languages they tested. And that's when they went in and decided to invent Erlang. They decided to invent their own language. And they took concurrency aspects from languages such as Ada, Modular, Chill, and Smalltalk. A bit of, they were heavily influenced by functional programming and by logical languages such as Prolog. Actually, the first Erlang virtual machine was implemented in Prolog. And actually, for 4 years, whilst they were prototyping on a virtual machine written in Prolog, as it allowed them to very, very quickly go in and change and adapt features. So what they did is they spent about 2 years evaluating existing languages, and they spent another 2 to 3 years inventing Erlang. And they prototyped telecom applications. And if they added a feature and the feature reduced the code base, they kept it. If it was a really cool feature but it didn't reduce the code base or add anything extra which the language didn't have, they threw it away. And the problem they were trying to solve is the problem of complex systems. So telecom systems are very, very complex. There's no downtime. You pick up the phone, you expect to hear the toot on the other end. If you don't, it'll probably make the front pages of newspapers. They have to be scalable. So your Erlang, well, your telecom systems need to handle massive peaks and behave in a predictable way when you've got these massive peaks. And last, they need to be maintainable. And maintainability is one of the key issues which, well, in the cost of the software cycle. So if you look at all the telecom products, 80% of the cost is support and maintenance. So if you think of these, all of these factors contribute or make it much harder to reach your time to market. But these are factors which are not just specific to telecom applications. They're specific to any server-side development out there. And you can think of web services, you can think of messaging, you can think of telemetry. So there are lots and lots of areas of applications. And in fact, when Erlang was released as open source, it left the telecom market and started making its way into the web, into gaming, into chat, and into a lot of other areas. And I think one of the main reasons for this is that the computer science lab went in, and they went in to invent a language to solve a particular problem. They didn't do like a lot of other language inventors do. They go out and invent a really cool language, then they scratch their heads. This is great, but what are we going to use it for? And then try to look for verticals. They were trying to solve a specific niche in the market. So what are the features of Erlang? First of all, it's declarative, and by declarative, they've done studies and they've come in to notice that it's about 4 to 20 times less code than your average code development in C++ or Java. And I'm going to give you some examples of it. And by declarative, well, we mean that there's a very, very high level of abstraction. You've got concise pattern matching and very, very readable programs. So let me just give you one quick example. I promise there won't be that much code, but here we've got an example of a function called factorial. And what we do here is we go in and we call factorial with, say, an integer of 2, and we try to pattern match the first clause. The first clause will fail because 2 doesn't pattern match to 0. So we go on and we try to pattern match in the second clause. The second clause, n is a variable. All variables start with uppercase letters. And so if n gets bound to 2, and we check, is 2 greater than or equal to 1? Yes, it is. So we return 2 times factorial of 2 minus 1. And so we do call factorial of 1. We try to pattern match in the first clause. We fail again. We go on to the second clause, and we get factorial of 1. And we then call 1 times factorial of 0. We hit the first clause again. That's our base case. That's where we stop. And we return 2 times 1 times 1, so, which is 2. Now, this is a very, very simple piece of code, but it's kind of very readable. And there's 2 more things I wanted to mention here. Now, first of all, you've got variables. They're uppercase. And variables in Erlang will be single assignment. So once you've bound them, you cannot go in and change them. And this is one of the things which will force programmers to write short, concise functions. The second thing is the lack of defensive programming. What happens if I call factorial with -1? Would it pattern match the first clause? No. Would it pattern match the second clause? N is unbound. We bind the variable to -1. -1 is not greater than or equal to 1. So what happens in this particular case is that the process or the actor executing this particular function would terminate. And by terminating, you'd lose the state of that particular process. There's a bug in the code, the data is corrupt, stop. And this lack of defensive programming allows the programmer just to think for the positive case. And I'm going to tell you a little bit later how it's actually handled. Here's another question. How many of you have implemented quicksort in any language? What languages have you used? C, okay. Java, Scala, okay. Assembly, whoa, kudos, respect, man. How many lines of code did you get in, let's start off with C. 30 lines, yeah. In Haskell, it's 2. This actually comes from Haskell. How about in Scala? 5 or 6, exactly. And the reason both Haskell and, Scala are considered functional languages, just like Erlang. And what we've done here is we've taken, quicksort, and we've implemented it using something called list comprehensions. We take a list, we call quicksort with a list, and we break the list into a head and a tail. So the head here is the first element of the list. The tail contains all the other elements in the list. We then go in and we take the element x, where x comes from the tail, and we want to make sure that x is less than or equal to the head. So we create a new list with all the elements less than or equal to the head. Underneath, we create a new list with all the elements greater than or equal to the head. So we're splitting the list in two. We call quicksort recursively on them. And when we get the results back, we append the first list, which gets them back, to the head, to the last list, and we've solved it. And actually, someone mentioned Haskell. List comprehensions came from Haskell. Haskell and Erlang are, well, referred to two childhood friends growing up. And at the time, I was at the computer science lab. We had Phil Wadler and Simon Marlowe walking in the corridors. Simon Marlowe did his PhD thesis around the type system for Erlang. And one of the things Phil Wadler convinced Joe Armstrong to add to the language was list comprehensions. And what actually happened was one day I was walking down the hall and Joe Armstrong, so the inventor, comes in. Francesco, come, have a look. And he goes in and he shows me this particular example. And he shows me funds and higher order functions and how you can abstract recursive patterns. So real nice, interesting features from functional programming. And he shows how you could compact your code even more. And Joe then goes, listen, go out and use this in your programs, but don't tell anyone about it. And didn't quite think that much about it until about 6 months later. An email comes out on the internal Erlang mailing list at Ericsson. So remember, Erlang wasn't open source yet at the time. And someone goes in and says, oh, cool, I found the ++ operator. Are there any other undocumented features in the language? And indeed, at that point, product management, the owners who owned the specification of Erlang, very quickly went out with a disclaimer email saying, any other non-documented aspect of Erlang might not be there in the next release. So what had basically happened is Joe had gone in and snuck in list comprehensions, funds, higher order functions in the language. Once he'd snuck them in, he'd gone in and told everyone about it. And that email created a whole flame war and a thread war because, oh no, we're using it, you can't remove it, it has to be backwards compatible. So the next release of Erlang came about, everyone wondering what's going to happen, and indeed list comprehensions were documented. So it became part of it. Another question, how many of you have decoded an IP, a TCP packet? How many lines of code? What language did you do it in?
I actually decode.
You decode it, yes. You're using Wireshark, okay. That's cheating. So if you were writing Wireshark, you'd want to do it. But let me give you an example. So a TCP packet consists of a header with 10 mandatory fields and an optional one together with the data. Now this example, I'm assuming now 32-bit words. So assuming we've got the packet here and we bind it to the variable segment, what I'm doing here is I'm pattern matching on a bit level. So I'm saying that in the variable segment, which happens to be a binary, so a chunk of untyped data, I want the first 16 bits here to be bound to the variable source port. I want the next 16 bits to be bound to the variable destination port. The next 32 bits to the sequence port, and so on. Here we've got flags. That's just bitmaps, and we say that the variable flags consist of the next 8 bits. And what we do down here is we take the flags, and we extract all of the flags, so CWR, ECE, etc., etc. And so with pretty much 1, 2, 5, 6 lines of code, we've decoded a whole TCP packet. Yes, you can actually specify it in your specification. Here we're just using the default value. So, incredibly powerful. I mean, one example is I was working on the ISO 8583 protocol with a bank at one point, and the developers were really, really excited. So the ISO 8583 protocol is the protocol your bank ATM machine speaks when it connects to the bank servers. So for every command, you're inserting your PIN, you're extracting money, you're getting your statements, you're checking your balance, will consist of a request and a response. And I was working with a team of programmers who had previously implemented this in C. And they were saying, oh, every request, every frame we need to decode is about 100 lines of C code. And Erlang is absolutely brilliant. It's great. They'd managed to cut it down to about 10 lines of Erlang code. But this was quite some time back, and they weren't aware of the ability to pattern match in the bit syntax. So what we did is we sat down, I'd say, yeah, this is great, but why aren't you using the bit syntax? Went in, explained it, did a bit of training, and when we were done, they went in, really excited, they went in and rewrote it, and they managed to reduce those 10 lines of code to about 2 lines of code. End of the week, they've basically gotten rid of about 80% of the code base they'd been working on for the previous month, checked in about 50 lines of code, and then started getting all worried. Project management would go in and do a word count on what they had committed. So if you look at it, completely readable, completely easy to maintain and debug. So this is it on the high-level constructs. Another really powerful aspect of Erlang is the whole concurrency model. Now, very, very early on, they decided to detach the concurrency model from the underlying operating system. So what they did is, they've got a virtual machine, which is in itself an operating system on top of the operating system. And the virtual machine will handle all of the scheduling, all of the preempting and suspending of process, as well as all of the process intercommunication. To create a new process in Erlang is really, really easy. You just call a built-in function called spawn. You pass it in a module, a function, and a list of arguments. And what happens is that it just goes in and creates a new process. And this process starts executing in that function with those arguments you've passed. Processes do not share memory. So if processes want to communicate with each other, they communicate via message passing. That means that the process here on the left has bound the process identifier on the process here on the right in the variable PID. And when doing so, it sends it a message of the format here, data 1213. So this is just a tuple, which is similar to an array. So it contains a constant amount of elements. And what happens is that this data structure here is copied from the memory, from the stack of this process to the heap of the receiving process. So what you're doing is you're actually copying the data in between processes. There is no shared memory. And the process on the other side will store the message in its mailbox. And whenever it goes in and encounters a receive clause, so whenever it can continues executing, and as soon as it encounters a receive clause, it will go selectively and it will go in and selectively try to retrieve the messages. The messages in its mail. It will pick the first message. It will try to pattern match it. If none of the messages match, it will go in and try to pick the second message. If none of those messages match, it will continue on to the third and so on. And if none of the messages match, the process is just suspended, and it waits for a message to come in which actually matches. So how many of you have implemented finite state machines? Okay. Have you had to deal with messages which come out of sequence? So if you think, if I'm to put on my telecom hat, telecom systems consist of incredibly complex finite state machines, protocol stacks which are not for the faint of heart. And you will get messages coming out of sequence. Have any of you guys had to, deal with them? How did you solve the problem? Sorry? A lot of hard work. Buffering, exactly. Buffering, round robin, you need to retrieve the message, you need to store it, and then the next, when you do your state transition, you need to check, is this the right message? Other people have actually added an extra state just to handle that event which comes out of sequence. In Erlang, with the selective receive, all you do is you just leave the message in the mailbox. You don't extract it until you're in a state where you can actually handle it. So it just reduces the code size drastically when you're implementing finite state machines. And it's no secret. When they were doing prototyping Erlang and were trying to invent it and create it, what they were doing is they were prototyping plain old telephony systems. So they were implementing a soft switch, a switch which in the software allows two phones to connect to each other. But key to the Erlang concurrency model is the fact that there is no shared memory. And I'm going to come back to shared memory in a second. Now, another thing which they've added in the semantics of the language is a very, very simple error recovery mechanism. So error handling and error recovery mechanism. And this is an error recovery mechanism which allows you to build much larger frameworks, which will then go in and handle your errors. So you might have heard of the let it crash philosophy. If something goes wrong in your system, so if there's a bug, or if your data is corrupted, and that causes a crash, let your process terminate. Don't try to handle it in the software. I mean, from experience, trying to handle bugs or unexpected events in the software just results in even worse, even more bugs being inserted in the system. So the Erlang way is just, if something goes wrong and something unexpected happens, let it crash. And this is what happens. So these are the error handling mechanisms which exist in the language. First of all, you've got links between processes. So processes can create a bidirectional link by calling a built-in function called link, or when you create a process, you could just link to it directly. And if a process terminates abnormally, it will propagate an exit signal to all of the processes it is linked to. So if this process terminates abnormally, it will send an exit signal to this process in the middle. That process will terminate and send 2 exit signals to the 2 processes on the left and on the right. They will terminate as well. So the whole termination is propagated. There will be cases where we want to catch the termination propagating. So you've got a process which terminates, it makes this process terminate, sends an exit signal to this process and this process, but as this process is trapping exits. Now, trapping exits is done by just setting a process flag once we've created it. What happens is, instead of terminating, it receives an exit message. So this message is just placed in this process's mailbox. This process can go in and retrieve it. It sees through this process identifier which process terminated, as well as the reason. And this process is then able to go in and handle and regenerate and recreate that process and restart it. And using the whole idea of links and trapping exits, we create supervision trees when we're implementing Erlang. Now, try to imagine a TV voting. So TV voting via SMS. I don't know if you have things such as X Factor here in Israel, or Dancing on Ice, or Dancing with the Stars. I know. My partner forces me to watch them as well, and so I feel for you all. And in the UK, all of the SMS voting for all of these crap TV shows goes through an Erlang-based system, and what happens there is that for every SMS coming in, which has to be counted, we just go in and we create a new Erlang process. You create a new process. Now, processes are cheap. It takes microseconds, less than a microsecond, sub-microsecond, to create a new process in Erlang, because once again, you're not relying on the operating system, you're not relying on I/O, and your basic process will take up a few K of memory, not more. So in theory, you can have millions and millions of simultaneous processes being handled in your Erlang virtual machine at any one point in time. So the way you would do it is, assume we've got a supervision tree here. Up here, we could have a process which is responsible for the databases, which handles all of the counters for everyone you're voting for. And then for every SMS coming in, we just create a new process which we hook to the right hand of the supervision tree. And this allows us to, describe dependencies in the code, because the counter here, the process handling all of the counting, is independent. If any of the SMSs here, any of the processes handling the SMSs terminate, we let them terminate without affecting anyone else. If a process handling my SMS crashes, who cares? Okay, my vote won't be counted, but we don't want the whole system to come down and crash. On the other hand, if the actual process which handles the counting itself terminates, there's something wrong. We want to terminate all of the SMSs, all of the processes handling the SMSs, and restart. And hopefully, by doing that, we will have cleared the state. Now, just to give you an example, it's very hard, to explain it here in a few minutes. But just to give you an example, they actually went in and have done studies in academic circles, and have taken a C++ application and rewritten in Erlang. And what they did is, depending on how you counted, they came to the conclusion it was up to 20 times less code when written in Erlang. One of the reasons And one of the things they did is they counted what every single line of code did. And on the C++ application, they realized that all of the error handling and defensive programming consisted of about 25% of the code. Can anyone guess the counterpart in Erlang? 1%. And the reason that it's 1% is that all of the error handling is actually put in library modules, which are provided for you, which we call supervisors. So it's something you don't have to worry about. It's something the system architect has to worry about when he looks at the restart strategy. So if a process terminates, you lose that process, you lose its state. The real challenge there is actually restarting that process, making sure that the state you recreate when you restart it is actually clean, because that might very well be what has caused the crash in the first place. Okay. Any questions? Yes?
Can you make a comparison of what you call a process to something Java or Scala? Or Java?
Yes. So when I talk about a process, so the question was, can you make a comparison about a process you call in Erlang to Java or Scala? So Java, well, in Java, if you want concurrency, you need threads. You need operating system threads. That means you're reliant on the underlying operating system, and you've got limits on the amount of scalability you're going to reach. In Erlang, what you do is, when you start your virtual machine, the virtual machine actually creates a thread for every core in the VM. And that's it. Every other Erlang processes are actually implemented within and handled within the Erlang virtual machine. So all of the scheduling, all of the migration from one runtime queue to another, that's all in the Erlang virtual machine. So by completely decoupling it, you're in fact cheating. You get concurrency levels which you can really not achieve with Erlang. Now the closest we can get to Scala to Erlang processes are Akka. So it's the actor model and it's Akka, which Jonas Bonner implemented of pure frustration. Jonas Bonner is the main developer behind Akka. And I don't know if you know the story, but he was, he started implementing Akka when he wanted to use Erlang on a customer project, and he wasn't allowed to. He had to use Java, and he wanted a lot of the concepts and principles from Erlang. So that's when he created Akka. And what I can say is, what you can do is by running the actor model on the JVM, you can get the libraries, but you will not get the semantics of the Erlang virtual machine. And it's actually the semantics of the Erlang virtual machine which makes Erlang's concurrency model unique and special. And it's very, very hard to simulate on the JVM. Because in Erlang, what happens is every process gets a few, about 1,000 operations it gets to execute, after which it's suspended and the next one gets to execute. You don't have that luxury on the JVM. The second thing is, in Erlang, it has a per process generational garbage collector. On Java, you're stuck with the JVM's garbage collector. Yep. So you've got quite a few. The Erlang virtual machine was built for massive concurrence, and it was built for fault tolerance, and that's and it's for those type of applications you should be using it. Yep. Yeah. Okay. We all yes. Yeah. Okay. That's a very good question. I'll get to that in a second. It's right. So the second. Let me finish the features first. Yeah. Now, another thing built into the language is Erlang distribution, and it's got a it's distribution built in the Erlang VM, and it's based on TCP/IP. And it's completely transparent to the programmer. So assuming you've got two Erlang virtual machines running next to each other, you've got two virtual machines running next to each other, and if you want to send a message to a process on the same virtual machine, you've got the PID, bang, and you've got the message, and that's how you do it. You want to send a message to a process on another virtual machine, it's exactly the same syntax. The only difference here is that the variable C contains the process identifier of the remote process on the other node. So by doing things right from the start or with very little changes, what you wrote to execute on a single machine will automatically run on a cluster of nodes. Hot code loading. Well, there was a really good talk about dynamically typed language, and Erlang is a dynamically typed language. So what you're able to do is actually do a hot swap of your modules in runtime, and you can do that whilst maintaining the state of your processes. It's an idea that actually stole from Smalltalk, which was doing it back in the 60s. And the concept is very simple. At any one time, you can have two versions of the module in the virtual machine. If a process is running a particular version, it will continue running that version, even if you load a new version in the Erlang VM. Now, when any new process which starts executing the latest version of the code. So if you're running, for example, an IVR, and you've got the whole kind of call setup and all of your menus, you want to upgrade. Any calls running on the old version will continue running on the old version. New calls which are created will be running on the latest version. Now, at any one point, if this process here does what we call a fully qualified function call, that means if it prefixes the module name to the function name, in doing so, a check is done. Am I running the latest version of the code? No, you're not. Bang. The pointer to the code is actually changed, and you start running the latest version of the code. And at that point, all of the variables and the whole state of that particular process is retained. And then finally, a few words about multi-core support. Until the last decade, you wanted your program to run faster. You waited 18 months. You bought a faster computer. Right now, if you want your program to run faster, you wait 18 months. You end up buying a computer with many more cores. But will your program actually run faster? In Erlang, the first release of Erlang on multicore actually came in 1996. They had a computer at the lab called Four Roses. And I think the biggest issue to scaling on multicore today with technologies is memory lock contention. The fact that Erlang processes have no shared memory reduces and removes a large number of bottlenecks you will have to multicore scalability. And the way they run is very simple. You've got your Erlang virtual machine. For every core, you've got a scheduler. And you just what you do is you just queue. You've got different run queues. And you just have different processes all running in parallel, each on each scheduler. And that gives you today linear scalability to about 16 to 32 cores, depending on your application. And there's research now to push Erlang for linear scalability to up to, to machines with millions of cores. The biggest challenge, obviously, is bottlenecks within your system. So I think that's where a lot of the research is going on. And just talking about how Erlang scales well on multicore, I mean, just that is a talk in itself, maybe for next time. There's a lot of, projects using Erlang. I think you heard about CouchDB last time. React, we heard about this morning. The Disco projects, it's a MapReduce project by Nokia Research. It's about 80% of the Hadoop functionality with 10% of the code base. Very, very popular within the Python circles. RabbitMQ, the MQP messaging broker, owned by VMware. Or Mongoose IM, which is, a scalable instant messaging server. It handles millions and millions of simultaneous connections. And with these examples, what is Erlang good for? Where should Erlang be used? Erlang is really good at coordination. It's really good at orchestration. It's really good when you've got a lot of activities all happening in parallel. That's when you should go in and start using it. You should not be using Erlang when you're, for example, dealing with number crunching, with low-level optimizations, with drivers. And you should instead use Erlang as the glue and then interface towards C or interface towards Java or your fast languages, which allow you to do all of that. The question is, why are we not all using Erlang? Well, here are just two quick slides over companies which presented at our latest events in the US. Erlang is widely used. Now, it is not as widely used as it should be because when Ericsson released it as open source, they released it very, very quietly. There was no PR, there was no Sun. They did not do what Sun did for Java. They released it as open source, and it started spreading when bloggers started paying attention to it. So then from bloggers, the first book in about 10, 15 years came out in 2007, and that's when we started seeing a very, very rapid adoption. At that point in time as well, the whole, all the conferences you went to, you'd get the free lunches over talks. And so the whole scalability of multi-core, companies who are aware today that they want to write software systems which will scale on multi-core architectures which still don't exist or not available commercially, started going down the Erlang route. And it's got quite a bit of traction now, especially it's getting more and more traction as we're seeing it now. We're seeing more and more users of it, more and more Fortune 500 companies adopting it. If you want to learn more, these are 3 of the books which I recommend. The first one is Programming Erlang by Joe Armstrong, the inventor of Erlang. And it's more about why should you be using Erlang. The second one is the one by O'Reilly, which I wrote together with Simon Thompson of the University of Kent. And that's if you want to learn Erlang in depth. And once you read either the first or the second, the third is how do you implement industrial systems. But those are just some of the books. Here are even more which have come out. So there are plenty and plenty of them. And just a little plug-in. We're now running a little Erlang track which starts at 4 p.m. And we've got Zach, who will be speaking about OTP, and he will be speaking about building Skynet. He'll be giving demos over the middleware we use when developing Erlang-based applications. And we've got 3 use cases. First, Alexander from Uvu. He's looking at Erlang for scalable instant messaging. Second is Lahav on about operations. How do you deal with Erlang in operations? And then third, we've got Z, and he's looking at the whole idea of a connected society and how MQTT and Raspberry Pi and Arduino kind of all fit together in a connected way. So 3 case studies plus a bit more on Erlang if you're interested, and we're in the room right here in the back. Okay. Any questions? Any more questions? Yes.
Erlang proved itself for the use case of instant messaging or anything high performance.
That is correct.
But if you're looking at Erlang as a general language,
I don't believe so I don't believe there is a general all-purpose language. I'm more of the belief that you want the right tool for the job. And we've seen, what's happened with Java as a general all-purpose language, or what's happened with C++ as a general-purpose language. It doesn't really exist.
so you're saying that the person that wrote the actual 3D model application,
Wings 3D, yes.
so that was a mistake?
No, that was a hobby project, which Björn Gusten, so he was the maintainer of the Erlang virtual machine who wrote Wings 3D. And he wrote it, but when he was doing it, he was actually behind the scenes, not telling anyone, rewriting the Erlang virtual machine to speed it up. At the time when he was writing Wings 3D, he was frustrated because all of the real number operations were really, really slow. So despite it not being on the project roadmap, because telecoms doesn't need floating operations, float number operations, doesn't need them to be efficient, they were strangely enough becoming much and much more efficient as he went along. So it's not a mistake. Of course you can do it, but it wouldn't be my first language of choice when doing something like that. I would have probably gone for C. When he did start, and that was early 2000. But yes.
You talked about how Erlang scales very well. So what I wanted to ask is, what about the support of Erlang on GPU?
So okay. So when I say Erlang scales very well, I mean Erlang will behave in a very, very predictable way under extremely heavy loads. So assume you've hit 100% CPU and you're running 10,000 simultaneous requests in your system, and you've gone with these 10,000 simultaneous requests, each request takes 1 second. With Erlang, all of a sudden you start running 20,000 simultaneous requests in your system. Your throughput will still be 10,000 requests per second. So the only delta there is that you will start getting, your request will start taking 2 seconds. So latency will go up. But your throughput will still be 10,000 messages per second. You will not see this degradation you will see in most languages. So that's the first clarification. The second, in regards to GPUs, there is research going on. Now, Erlang has never been used for number crunching. Erlang should not be used for number crunching. There are much better tools for it. But what you want to use Erlang for is the glue for it. Now, on the GPU side, there is a research project going on right now where they've actually managed to where they've hooked into the GPUs, they've hooked into, say, OpenCL. So they've got a lot of these libraries which take care of all of the, which really use hardware optimization. They're C libraries. And what they're doing is they're looking at Erlang code, they're refactoring, they're looking for patterns, doing static analysis, and then refactoring the code to actually utilize GPUs. And have you heard of the Parallella board? Raspberry Pis? Okay, so what we had is we had 4 webcams connected to Raspberry Pis, and then we had a Parallella board. A Parallella board is nothing other than a Raspberry Pi, but with 16 cores, same size, $100. So you can buy, in June you'll be able to buy for $100 a machine with 16 cores. And it's, which consumes 2 watts of energy, by the way. So we were running Erlang on it. So what we're doing is we're getting 4 streams from 4 webcams onto the Parallella board, and using specific hardware optimizations and GPUs, we were actually able to track the ball on a screen with 2 watts of energy. So it's getting there, but it's still research right now. Yes?
I have a question about, can you use Erlang for web development?
So the answer is yes and no. So there are only 2 areas I would use Erlang. I would not use Erlang to build a website, even though you have content management systems for Erlang, which are getting much, much better. But you want to use Erlang for RESTful APIs. In fact, I think a great example we saw earlier today was React. React has a RESTful API, and React is 100%, well, 190% Erlang. That's the first area where you really want, Erlang excels at. And the second, where it's really getting in and becoming mainstream, is WebSockets. And just to give you an idea over why Erlang would be suitable for WebSockets, you all know of WhatsApp. Yeah. So WhatsApp is an Erlang shop. And to reduce the operations cost, they've really pushed down, they've really pushed up the number of users on a single machine. They're actually running on a single machine 2.5 million open TCP IP connections. And so they're running about 2 million users per machine, and simultaneously connected users per machine. Actually, WhatsApp have a higher active user base than Twitter these days. So they surpassed Twitter last month. So every TCP IP connection is just an Erlang process.
Why you cannot, let's say, you cannot develop website, so it's not a good idea. But I just don't understand.
So the reason it, yes, so this is the last point. The reason it's not a good idea is that you do not have all of the libraries. So you need to go in, yes, exactly. There are no libraries for Erlang. And, and I think it's a lot of work to go in and recreate what you've got, for example, with, PHP BB for, the media wiki, take WordPress. I mean, there's no reason. I think if you look here, the erlangcentral.org is a community site. And just to advocate the right tool for the job, we're using a mixture of PHP, Erlang, and other technologies as well. It's not 100% Erlang, because we would not have been able to pull it off with such little resources. So the chat's all Erlang. A lot of the agents which go out and create news is all Erlang. But we've just taken PHP BB and WordPress and the media wiki straight out of the box. Brilliant pieces of software, and just integrated them and started using them.
We can say, for example, about Node.js, right? There was, when it was born, JavaScript, whatever, right?
Yeah.
There was no basically framework, TTP framework. There was only
Yes, but they were. Yeah. So I need. Yeah. Let's continue. Let's continue after. Raf is coming on. All right. Thank you very much. Thanks.